Hello everyone, welcome to Tech Talk session number 18. An amazing amount of Tech Talks to date. Welcome to Tech Talk session 18. This is a part 2 Tech Talk where we're going to continue to talk about harmonic analysis. Knowing the basics is essential. Before we get going, I want to welcome the international participants. We've had people from India, Europe, South Africa, Chile, Peru. So this is pretty exciting. The participation continues to grow. We also note that each and every night that there's a good 50 or so views at night. So please continue to share the NEPSI Tech Talks with your colleagues and talk about and get them to also view the presentations. So we're getting on with the presentation today. It's a continuation of what we did last week, and we're going to end up recapping what we did last week just for a moment, spend about 5 minutes, and then we'll get into the presentation today. So don't forget there are PDH credits available at the end of the presentation. We will give you a code. Feel free to send that email to either myself or to Matt, and we will give you some PDH credits for it based upon the amount of time of the presentation. Don't forget to ask questions. When you do ask a question, Matt will chime in, and he will narrate the question to me, and we will try to answer questions as we move along. We're trying to make this more interactive, the presentations, so we're hoping that we get more participation. Go to the chat box, ask your question in the chat box. And finally, don't forget what NEPSI does. We want to make sure that, well, let's move on with Rodrigo first. I'm out of order. So this is another thing that we're going to be starting next week. Rodrigo Dunner, our International Business Development and Sales Manager in South America, located in Chile, will field questions in Spanish. So for those in Spanish-speaking world, feel free to ask questions in Spanish. When you do ask the questions, Rodrigo will pop up on the screen, and together we will answer your technical questions. So this will be something new next week that we add. I think it's a pretty exciting addition. So we're looking forward to doing that. And then finally, don't forget what NEPSI does. And this is what NEPSI does in a nutshell. We design, build, and commission metal enclosed harmonic filter systems between 2.4 kV and 38 kV. And also, of course, don't forget capacitor banks, metal enclosed capacitor banks. So this particular project here, it's a 34.5 kV, 200 kV BIL, 27 megavar harmonic filter system. And there's 2 such filter systems located here that were put on concrete pads. So this is a complex harmonic filter system common for the mine projects that NEPSI gets involved with. They're multi-tuned, consisting of C high pass and high pass type harmonic filters. In particular, when we are selling into South America, we're dealing with high altitude, and therefore impulse level becomes a critical matter. So this is just a bit of a showcase of what they look like, and here's another close-up view of it. One of the advantages of the metal closed solution is this compact, very compact solution. You can even see in this picture here, the perimeter, there's a cliff around this. They had to blast the rock out to fit this. So if this were an open air solution, it would take an area of about 4 to 5 times the area shown here, and it would be much more expensive to install. So the metal closed solution is quite applicable in the mine environment, especially in South America. So in case you missed last week's presentation, you can view it on our YouTube channel, youtube.com/NEPSI. We'll get you there. There is a playlist for each that contains all the tech talks that NEPSI has done in the past. So we're at number 18 now. So let's go through what we did last week. So last week we talked about harmonic analysis. We talked briefly about the concept of how a study is conducted, and we're going to go through this very quick, why harmonic analysis are produced. And just quickly, we're doing harmonic analysis because we're looking for or to determine compliance with IEEE 519 or some other type of standard. It may be a new facility or it may be an existing facility that's adding, say, nonlinear load. We're looking to calculate voltage distortion and current distortion within the plant environment. So what is the voltage distortion? What is the current distortion? And really, when you are doing harmonic studies, inside the plant, voltage distortion is the key area of concern. Remember, we're typically designing for 5% VTHD inside the plant. So we do our analysis, we determine the voltage distortion, and we say, okay, what is it? We're trying to achieve 5% or less. In terms of current distortion, we're looking at what's going on at the point of common coupling, at the incomer to the plant. What is that current distortion? And really that involves trying to determine compliance with IEEE 519 or some other type of standard. And we also do analysis to determine or to evaluate resonance concerns. Will we have a harmonic resonance if we install capacitors? Remember, you're installing capacitors for power factor correction. The question becomes, are you going to have problems when you install those capacitors because of resonance? And this is part of harmonic analysis. And then finally, if you do have problems, or if I have harmonic current distortion issues or high voltage distortion issues based upon the analysis, you actually use harmonic analysis to evaluate a filter design in its performance requirements. It's part of the design process. So we talked about linear loads versus nonlinear loads. The top waveform here, we had a linear waveform. If we inject or if we put a sinusoidal voltage across a linear load, we get a linear current. The bottom waveform here, we see that if we put a sinusoidal voltage in it, we get a square wave current. And the question becomes, well, how do you do that analysis? And really it involves doing harmonic analysis using the Fourier transform. We take that this square wave and we can decompose it into many sinusoids. And what that does is it allows us to do standard network analysis. So what it's doing. So in a sense, we can build an impedance model and do standard network analysis, just obeying by the impedances of the elements within the equivalent circuit. So we take a three-phase circuit here, we develop a single-phase model, and we basically apply Ohm's Law. And that's kind of what we talked about last week. We talked about the fact that there are harmonic current injections. Those harmonic current injections are ideal current sources, meaning that no matter what the impedance there is, no matter what this impedance here is, this harmonic current will stay the same. These harmonic values are based upon drives or based upon the harmonic producing device. You can get that data based upon the device that you're using. If it's a 6-post, 12-post device, if it's an active front-end drive, you can go to the manufacturer and get that data, or you can take measurements at the system. But in the end, it's important that you get the harmonic current injection as part of the model. And also don't forget, we're evaluating current distortion and voltage distortion at the point of common coupling. In this case, I'm showing IEEE 519, but there are other standards that apply. So just kind of going back. So we took a standard system and we developed the equivalent model for it, and we reduced that to a single impedance, and we developed a straight line impedance curve here, which is basically the impedance looking into the circuit here. Okay, so we're looking into the circuit here, we develop an impedance, and that's that straight line. So we got harmonic number versus ohms here. Okay, so a Thevenin equivalent is what we're looking at. All right, so moving on. You take the harmonic current injection here, multiply it times that impedance line, and we can get voltage distortion using these formulas here. So basically, V equals I times Z. And we're moving along fast here. Don't forget, the recording is recorded. You can view Tech Talk session 17, the whole entire presentation. When you add capacitors to the system, we get a issue of resonance, and it's because the capacitor reactance, the green curve, will drop with frequency, while the source impedance will increase with frequency. All right, so here we show that we do have resonance when we install a capacitor. Because we have resonance, we have this high impedance. This magenta curve creates a high impedance. That high impedance is only limited by basically the resistance of the circuit, and therefore it can be very high. It's about approximately equal to x of c squared at the harmonic frequency or the harmonic resonant point squared divided by the resistance. We all know that resistance of the network is very low, and therefore it can be a very high impedance. that harmonic current injection times that impedance creates a lot of voltage distortion, and this is the concern. So we get the harmonic current times the harmonic, the impedance gives us the harmonic voltage. That harmonic voltage is line to neutral here. So we also talked about that when you do calculate resonance in the resonant location, you have to realize that you can get shifts in the impedance curve, and there are various things that can cause that shift. Short circuit impedance changes because of the amount of motors that are connected to the network, or the source impedance up at the transformer, and even the tap changing portion of the transformer itself can have an effect on the impedance. So it's important to realize that when you do calculate resonance and you get a value of, in this case, 5.59, that it doesn't clear you of having any types of issues. You still may have issues. And when you do your analysis, you should be doing a sensitivity analysis to make sure that any type of shift in your impedance curve or in your resonance will not result in a operating condition that is not good. We also talked about the fact that when you do apply what I would call IEEE 519 drives or active front-end drives, that you still have a concern. There's still a concern for harmonic resonance. Even low-level harmonic current injections from these high-pulse drives or these IEEE 519 drives can still produce a fair amount of voltage distortion. And in this case, with the sample problem, we calculated something on the order of 52% for one type of drive and 33% for the other. So the concern still exists when you are producing, when you have an active front-end drive or IEEE 519 compliant drive. When you think about tuning around resonance, remember that the resonance, the resonant peak has basically shoulders, and that the end result is when you do add capacitors, you are going to most likely increase the impedance somewhere in the network, and the result will be to increase voltage distortion. So generally speaking, putting capacitors on the network will result in increasing the voltage distortion in your facility. We talked about parallel and series resonance. If you're on the secondary side here, you looking into the circuit, you have a parallel circuit, which is this path here and this path here. But if you're on the secondary side, you just have series resonance. So there are things called parallel and series resonance. The calculations are very similar. But the concern here is when you have a multi-voltage level industrial power system, where you have low voltage system and medium voltage systems, you want to be careful about scattering capacitors throughout that facility, because it can create a very complex impedance model. So we typically recommend correcting power factor at just one level. For multi-stage cap banks, a common application, the issue of harmonic resonance becomes multiplied for each stage that you have, and therefore as you switch stages on, you will cross through resonant points. If those resonant points correspond to any of the harmonics, you will have an issue. In this case, we cross over the 11th for the 1 megabar stage, and the result is that the distortion would be at 55%. So we might be okay with stages 2, 3, and 4, but in this case, for sure, stage 1 was not good. When you do have a resonance, you have current amplification. We talked about that. That current amplification can be very high. In this case, we're showing about an 80 times multiplier at resonance, and that is why you have fuse operation. Okay, so the red area here shows that amplification of current. The application of capacitors results in basically magnification of current through the point of common coupling, and oftentimes the addition of capacitors can result in you falling out of compliance with the distortion limits dictated by IEEE 519 and other type standards. So what about adding capacitors as harmonic filters? And this is where we left off last week, so we will slow it down from here. Here we're showing the installation of one of our harmonic filter systems. And when you think about the installation of a harmonic filter, or what is a harmonic filter, basically what we did is we added a shunt reactor to the capacitor bank. Same capacitor bank as before. but we added a shunt reactor up front. The filter bank is capacitive by nature. It is putting out VARs just like a capacitor bank does. So a primary rating of a filter bank is megavars or kVAR. It's this kVAR output. It happens to be the #1 reason why you install capacitor banks or filter banks on a system. You're looking for reactive compensation. Just to show you kind of a picture of a harmonic filter reactor, this blue one here is an example of a harmonic filter reactor. We had a pretty in-depth Tech Talk session 11 where we talked about harmonic filter reactors. So I encourage you to view that presentation to understand more about harmonic filter reactors and what they do in our harmonic filter systems. But before we get on to what happens when we install harmonic filters, let's just talk about why, or the primary reasons why you install harmonic filters on the system. The first one is by far reactive compensation. Okay, we're looking to provide megavars to the system. So megavars is the main reason. Power factor correction. All the reasons you do power factor correction are one of the reasons why you would install a harmonic filter system. You're looking to prevent resonance, and this is a second primary reason. And so typically what we see is that we had to add capacitors to the system to do power factor correction. And now the issue is, okay, we have resonance, so we are looking to prevent resonance. So what do? We add a harmonic filter. Okay, so the filter may not be added for the purpose of filtering. It might be added to prevent resonance. So we want reactive compensation. We don't want resonance. We add a filter. Second reason. Third reason is we have a large drive. We need to filter or pull harmonic current from the system, and that would be a second reason. So let me see if I can fix that. Yeah, no, that's not making it better. Okay. So we have harmonic filtering as a third reason. We need to pull harmonic current from the system, and then the fourth one is preclusion or resonance. So we'll talk about some of this as we move forward. So Tech Talk Session 9, we talk about harmonic filters, and I would suggest you also go to that Tech Talk to learn a little more about harmonic filters. In fact, the next 2 weeks we will be talking about harmonic filter design. But in Tech Talk Session 9, we talked about filter design using NEPSI's spreadsheet tools. And we will be doing a more in-depth discussion of harmonic filter design for the next 2 weeks. So we go back to that system, and we've installed a reactor here, okay, in series with the capacitor. Now that reactor is typically 1/n², about 1/n², the capacitive reactance of the capacitor. So therefore, at the fundamental frequency, the system is capacitive and it is putting out megavars. When we add the reactor to the capacitor, the result is we get an impedance curve that looks like this magenta curve. So what you can see is that the tuning point is in this case, is the 4.8, okay, because this is a 4.8 tuned filter. X of C equals X of L at the 4.8 harmonic, okay, and the result is we have a very low impedance at that point because X of C equals X of L, they're equal and opposite. So the only impedance that you will see through this network at its tuning point will be the resistance of this leg. So the resistance of the reactor and the resistance of the capacitor. The resistance of the capacitor is essentially 0 ohms, almost 0 ohms. The resistance of the reactor is about, for an iron core reactor, is about 100. X over R is 100. So take the value of X, the reactance, divide by 100. That's the resistance. So it's very, very low. And that's why it appears that the impedance looking into the network goes down to 0. An interesting thing is that you have what we call the anti-resonant point here. Whenever you install a filter in a system, you will always have a resonance that exists below its tuning point. Okay, so if I add 3 filters tuned to different frequencies, I will have 3 resonances that all exist in the system below their tuning points. So you introduce a resonance in the system. The key here, though, is that I've picked X of L here and X of C here, and I've dictated that they are equal at the 4.8th harmonic, which means that the resonance that I have will exist below the 4.8th harmonic. So if we look again at the harmonic current flow here, we took these harmonic currents, just to refresh you here, and we put them on the curve here, and we've injected those into the impedance here. So it's that value of amps times the value of the magenta curve, and you would get the value of volts. All right, so we do that at each and every harmonic. Obviously, in this case, where the harmonics are located, we have no resonant condition, and therefore the voltage distortion is low. In fact, the voltage distortion is lower than our first transformer line that we drew, that dashed line. So that's a good reference line if you think about it. This is the optimal, basically the lowest voltage distortion I would get if I had no resonant condition. I installed a capacitor, I got resonance, we showed that, which resulted in a very significant increase in the impedance. But in this case, I've installed the capacitors, I tuned it to the 4.8, and I pushed my resonance down below the 4.8, and as a result, I have low impedance at all the harmonic levels I have. So incidentally, the rule of thumb here, and really that's the key here, there's the rule of thumb, is normally your first tuning point is at the lowest harmonic that exists in a network. And most oftentimes, this would be the fifth harmonic. But sometimes it could be the third or the fourth harmonic, and in this case, we would see fourth harmonic filters or third harmonic filters, and even sometimes second harmonic filters. We're looking to control resonance by using the tuning point. We're controlling where it occurs by using the tuning point. And this is the fundamental principle of harmonic filter design, is to determine, well, where are my harmonic filters, and then to put the tuning points such that the resonance that's created by that filter is below any major harmonics or between major harmonics. Another thing we're looking to do is we're looking to create a low impedance path for the harmonic. So if I tune this to 5.0, for instance, it would be basically a short circuit at 5.0. Fifth harmonic current, all of it would flow into that filter branch. All right, a question.
Yeah, Paul, you have a question from Syed. He says, why is 6% reactor used as a typical series reactor?
Well, that's a good question. So 6% reactor, the first thing you have to do is, well, what is a 6% reactor? And if I take 0.06, so I'm taking 0.06, and I invert that and take the square root. That's a 4.08 tuning point. So the percent reactor is more of a European practice to call reactors out by percent than it is a North American practice. But a 6% reactor would have a tuning point of 4.08, and we would typically refer to that as a detuned capacitor bank. So in particular, for typical systems that are just using VFD drives, oftentimes there's a desire, or there's a concept that people have, is to put a 4.08 filter in, a 6% reactor, in other words. But a 6% reactor, do realize it's tuning the capacitor bank to the 4.08 harmonic. The concept there is that the filter impedance at the fifth, okay, will be sufficiently high such that no harmonic current will flow into the filter. Okay, so a detuned capacitor bank we're going to call it a detuned cap bank. But in a sense, it's still a filter. It's a filter tuned to 4.08. So, but a 6% reactor will tune the capacitor bank to the 4.08 harmonic, and that impedance, okay, and you think about it here, we're going to shift that to the left, which means that we'll be further up on the impedance curve here. It means less harmonic current will flow into the capacitor, and the result is it will become less of a filter and be more of a capacitor bank. And that's really the concept here. Personally, I don't like the concept of this 6% tuning or the detuned nature of it, because really the amount of harmonic current that flows into the filter branch or into the detuned cap branch is really dependent upon the ratio of the source impedance to the filter impedance at the fifth harmonic. It's just a current divider. When you come right down to it, it's a current divider. You could calculate the impedance at the fifth of the filter, calculate the impedance of the source at the fifth harmonic, and you could calculate the current divider. How much current will come from here, flow into the filter versus here. Okay, so there is a common notion that people have is that detuned capacitor banks do not result in overload and they do not filter. They are just there to prevent resonance. The reality is, depending upon the source impedance, a significant amount of harmonic current could flow into a detuned cap bank and cause it to overload or cause it to overheat if you exceed its rating, the reactor rating. So that is a good question. In fact, we were going to address the detuned versus tuned filter concept, or detuned cap bank issue. But it's really a low voltage, more of a low voltage concept than it is a medium voltage concept. So a good question. Thanks for asking. So we're putting filters in. So just to recap, we're putting filters in. We're tuning to, say, the fifth to create a low impedance so that current from the harmonic current injection or the drive itself will flow into the filter branch rather than into the source. So we're reducing current at the point of common coupling is what we're doing. And so we're reducing distortion at the PCC. And of course, if we have lower impedance at the harmonics, as we show here, we will have less voltage distortion. So V equals I times the value off the curve there. We obviously would have less distortion. So in this case, we dropped to 1.5% VTHD. So you do have this concept of multi-stage harmonic filters, and it's good to understand what happens here. We can have, in this case, we have a 1, a 2, and a 3, and a 4 megabar multi-tuned harmonic filter system. And you can see the tuning point never changes, okay? But what does change is that resonance that exists below the tuning point. Here we have resonances that as we increase stages, the resonance creeps. It creeps back towards the fourth harmonic, and then sometimes potentially even the third harmonic. So you brought up earlier this detuned cap bank issue. If you tune to 4.08, it means that this resonant point here is actually further back. And sometimes it can push back to the third, and there are concerns, always concerns, about third harmonic current being present in the network. So something for you to think about there is, okay, am I going to have a third harmonic resonance issue if I use a detuned cap bank, or one that's tuned to 4.08, or this so-called 6% reactor concept. So as we add more filters, you can see down here, we're basically adding branches in parallel. Our filtering improves. So it's a concept that as I add more filters, I'm adding more parallel branches, and therefore I'm reducing the impedance of my filter branch, and more harmonic current will flow into it. So multi-tuned filters, the tuning point remains somewhat stationary, but there is still this resonant point here that's really determined based upon the source impedance and the filter bank impedance. And okay, another question.
Yeah, Paul, new question. He says, are there specific things about low voltage passive filters? What's the reason that they're rarely designed and utilized?
You said rarely designed?
Rarely.
Well, so in the low voltage industry, which I was involved with 25 or 30 years ago, the low voltage industry basically standardizes. They will standardize on this detuned concept, 4.08, 6% reactor kind of a thing, or they will go with 4.8. But almost always, it's a 50 kVAR step, 100 kVAR step. This is what we have seen in the past, is 50 kVAR steps and 100 kVAR steps. It's a matter of more of a mass assembly kind of thing, off-the-shelf design concept. It is an issue though when you do have harmonic producing loads that are non-characteristic or not standard. Is it's difficult for people to go out and find a manufacturer for that harmonic filter. The majors like General Electric and Schneider and Eaton are producing these off-the-shelf type filters, and you're stuck basically with what you get. Getting a custom designed filter is more difficult to do at the low voltage level. At the medium voltage level, everything is custom designed. There is no off-the-shelf concept that you have at the low voltage level. Okay, so let's talk about this concept of multi-tuned harmonic filters. So here we've taken that 4-stage bank, which was a 1 megavar for each stage, and we instead tuned it to 4.7, 6.7, 10.7, 12.7. So if you look at this curve, you can kind of see what we got. We have the first tuning point here, 4.7. The impedance drops very low. We have 6.7 here, then 10.7, and then 11.7. Oh, wait, no, wait, 10. Yeah, 10.7, and then 12.7. So no, 11.7. Well, I'm messed up here. So 4.7, 6.7, 10.7, and 11.7. So that's a multi-tune harmonic filter. Obviously here you can see that we have significantly dropped our impedance relative to that transform impedance line. So we are going to have more harmonic current flow into the filter branches because we have a much lower impedance. So in this case, the distortion would drop to 0.6%. I've taken those harmonic currents and multiplied times the value of the magenta curve, and I come up with these values of voltage distortion. All right, so we are able to improve the performance of the filter by tuning at these higher harmonics, at the 5th, 7th, 11th, 13th harmonic essentially. There are some issues though, and I think we should talk about some of the issues with multi-tune filters. If you look at first of all, you look at the magenta curve, you see that there is a resonance that is produced by each filter branch. So that 5th filter produced this resonant branch here, and the next resonant point over, which is around the 6th harmonic, is produced by that 7th harmonic filter. And incidentally, we would call a 6.7 tuned filter a 7th harmonic filter, and a 10.7th harmonic filter, a 11th filter. So we get a resonant point for each one of those tuning points. If there were harmonic currents at those locations, it would obviously be an issue because it would be that current times that high impedance. So this is one of the concerns with multi-tuned filters. If you have any type of interharmonic resonance, it's an issue. So think about those conditions, cycle converters, arc furnaces, things like that that produce interharmonics are definitely of concern. And you can take care of that with a high pass or a C high pass type filters, and we'll touch upon that in a moment. The other thing that you need to worry about is if I have a multi-tune filter and say I were to lose the 5th harmonic here, or to lose this 5th harmonic filter here, what would happen is this 7th harmonic filter could potentially still be on, the 7th, the 11th, and the 13th, but this 7th harmonic filter is producing this resonance here. And it's very likely and very possible that that resonance would shift over the 5th harmonic. So for multi-tune filters, if you lose the 5th harmonic filter, the 7th harmonic filter that remains online could potentially shift over the 5th harmonic, and you could have a resonance concern. So multi-tune filters tend to be less reliable because of this issue. If I blow a fuse, say, or operate a fuse on the 5th harmonic filter, or the filter reactor fails, or I have an overload condition on that, and we trip it offline, The seventh filter may result in a fifth resonance, and the result would be a very high impedance times the fifth harmonic current that exists on the system. I would have a very high THD, and the whole system would trip on high voltage distortion. So there's a general rule of thumb is that you cannot operate the higher stages. You cannot operate the seventh stage while the fifth is offline. You can't operate the 11th harmonic stage while the seventh is offline. You can't operate it is wrong. 10.7, 12.7. That's why I'm keep having a problem. So it's a 12. It should be 12.7, 10.7, 12.7. So the 12.7th harmonic. So if I'm always making sure that the lower frequency filters are on. Okay, they're on before the upper frequency filters are on. So it's interlocking. We have an interlocking concept. It's important that you design reliable lower frequency filters because the loss of one of those could result in the complete shutdown of the harmonic filter. And the other thing is, if you're a filter design engineer, your desire should be, I want to design a harmonic filter using one tuning point first. That would be my recommendation because you're looking to build a most reliable or more reliable design. So if I have all my stages tuned to the 4.7th harmonic and I lose one of those filters, it does not matter because I have the other filters there. I can continue to operate those. In a multi-tune situation, it's not the case. If I lose my fifth, I got to shut the entire filter down. So for a process plant where you might be using a very large rectifier, you're going to typically see 5th, 7th, 11th, 13th harmonic filters. In those situations, it's very important that that 5th and 7th and 11th and 13th filter be designed very reliably. Otherwise, you potentially could have to shut your plant down, and that would be something that would be discouraged. What about stray capacitance? And in this situation, what we show is a harmonic filter, and it's tuned to the 4.7th harmonic. So I can look at this curve and see what's going on. I've got a resonance here. It drops down to 0 or 0 ohms just about, and then it comes up like this, and we have another resonance here. So this is very typical of a system that has a filter on and some cable capacitance. And so you'd see this most definitely in a renewables plant, wind farm environment where you have many miles of collector system cable. That cable capacitance might add up to a megavar or 500 kvar. It creates this resonance here, and then I got my tuning point here. So this is one type of issue that you sometimes have to design around. I have this very high impedance here. Even very low levels of harmonic currents at these tuning points here can result in a lot of voltage distortion. So sometimes a very common problem, especially in the renewables area. Another thing that we often see is a harmonic filter is installed on the system, and the concept here, the customer will say, okay, I install a filter, I've corrected the harmonics problem, and now I can install less expensive capacitor banks. And this is exactly what happens when you do that. You got your filter here creating that low impedance tuning point, and then we have the second resonant point here created by the capacitor bank. And that capacitor bank is going to shift around. If you had more stages, it would move around just like it did before when it was just a standard cap bank. So there's a basic rule of thumb is do not apply capacitor banks where you have notch-tuned harmonic filters. They don't mix well. They're kind of like oil and water. You avoid that application criteria. Our first question when somebody says they want a harmonic filter is, are there other capacitor banks on the network? If they say yes, our next statement is you have to take all those offline first and replace that megavars that you've taken offline with the harmonic filter megavars. Okay, so basically on an electrical system, you want all filters or you're stuck with all capacitors. And this is a basic rule of thumb that you want to follow. You cannot go with the concept that the filters will correct my problem and then go and then go install capacitors.
Hey, Paul, new question.
Right.
Asking, are multi-tuned filters made of a single branch or multiple branches, each tuned to an individual frequency?
All right, good question. So the answer to that is each, I'll go back to, maybe I can go back to this slide. Actually, maybe, let's do this. Let's try this. I'm going to try something new. Over here would be a multi-tuned filter. So this is a new concept. So this would be the filter, and a multi-tuned filter would be exactly this. So you got the reactor and the capacitor like this. So there might be one MVAR, and then 1, 1, 1. So it'll be a total of 4 MVARs here. Each of these reactors are going to have a different impedance associated with it. So it might be a 5th, a 7th, 11th, and then a 13th harmonic filter here. So this is how it would look. We might have a switching device up front here like this. And then, of course, we got fuses and the capacitor branches here. So this would be a typical multi-tuned filter. So, and these are all interlocked as you go up. So this is kind of the concept. And so good question. They all get separate branches. They're not part of the same branch. Okay, so, okay, go. Oh. Okay, so let's just talk about the filter branches for a moment. Here we have a fifth tuned filter, and incidentally, we don't always design to a 4.7th harmonic. Sometimes we would design to 5, sometimes we would design to 5.1 or 5.2. The choice of tuning point at each and every frequency is really dependent upon what you are looking to achieve in the harmonic study. How good does the tuning point need to be, or how low the impedance needs to be at the harmonic frequency right here? This is part of your design concept. If you have a system with a lot of harmonic current, you can't design to the 4.7th harmonic because you're already too far from the harmonic. I'm not going to pull in all the harmonic because there will be some impedance at the 5th harmonic. And I think if I go back to a little bit, I can kind of show the concept here. Here, in fact, we're showing it. This is not tuned to the 5th harmonic. You can see that there's a little bit of impedance there. And that's because we're not tuned right to the harmonic. So we don't always design filters tuned to 4.7. Sometimes it's 5.0 or 5.1. And there's reasons sometimes why we go above. So it's part of the process of designing the filter in the harmonic study is what are you trying to achieve? What performance are you trying to get to? So this is a notch filter. So I'm basically injecting 1 amp of current into the filter at each and every frequency starting at the fundamental, and I'm creating this impedance curve. And you can see at the tuning point it's very low, basically limited by the resistance of this circuit here, which is really determined by the reactor. X over R of the reactor for iron core is around 100. And for that of an air core would be typically in the order of about 60. Okay, if you got to kind of come up with a number. The system below the tuning point here is capacitive, and then above it is inductive. Okay, so there's inductive up here, capacitive down here. So at fundamental, it's a capacitive circuit and it's putting out megavars. And once you cross over the tuning point, it becomes inductive. So if we have a high pass, in high pass filters, we put a resistor across the value of X here, or the reactance. And in this case, obviously as you go up in frequency, X of L will go up basically linearly with frequency. So when I have at the 5th harmonic, I have 5 times the impedance than I do at the fundamental. So the resistance, though, it does not do that. As you vary the frequency, and you go up in frequency, the resistor will remain at a low value. So you get this effect of the impedance dropping off at higher frequencies, and therefore, depending upon the shape or depending upon the value of resistance you choose, you can get different shape impedance curves for the same filter. So this is a high-pass harmonic filter. Sometimes it's called a damped harmonic filter. And next week we're going to talk about how these filters are designed, and we'll talk a moment about why you might want to use a damped or high-pass harmonic filter over a notch filter, for instance. But just realize here that if I were to bring R to an infinite value, it would be a notch filter, and I would have this blue curve here that kind of looks like a notch filter, if you think about it. But as I decrease R, I get this more relaxed curve here, where I get better performance at the high frequency range. One key thing to note here, though, is a high-pass filter, when the value of R is dropped, okay, when the value of R is dropped, my filter tuning, the impedance at the filter tuning point will goes up. So it means that a high-pass filter, as you dampen it more and more, as you decrease R, the amount of harmonic current that actually flows into the filter drops off. It drops off as you decrease R. So it is actually one way to control how much harmonic current will flow through here at the tuning point, is to put a resistor in there. It's kind of backwards to what you would think, but it's the fact of the matter. So lowering resistance actually will decrease the amount of harmonic current flow through the filter. Now, obviously, as we decrease R, we will get higher frequency, lower values of impedance at the higher frequencies, and we will get more harmonic current flow there. So there's another type of filter called a C high-pass filter, and in this case, we've inserted a capacitor right here, and the concept here is X of L and X of C here are equal at the fundamental. So we choose a value of capacitance here, such that X of L equals X of C at the fundamental. And then the entire filter branch, X of L, X of C, 1, which we sometimes call the aux capacitor, and X of C main, which we call the main capacitor, that entire system is tuned to a harmonic. So it sounds complicated, but with the NEPSI spreadsheet tool, it's very easy to do. But we do this because sometimes we want to drop the value of R here to a very low value. We want to get what I would call a super damped harmonic filter. And to get that super damped harmonic filter, using a high pass here would result in a very high value of losses. Remember, the losses on that resistor is V squared divided by R. And the volts on that resistor is basically the voltage drop across the reactor. So if we go V squared over R is in the denominator, we're going to get a very high value of losses. So if you go to this type of filter, it's still a high-pass filter, but at the fundamental, we've tuned X of C and X of L together here to 50 or 60 hertz, the fundamental frequency, and the result is 0 volts across the resistor, which means I have no fundamental losses. So I am able to get a super damped filter with no losses. And typically, second, third, fourth, fifth harmonics is where we would see the application of these types of filters, and it really is a great type of filter to use when you have to use it. So we recommend it. So let's talk about, well, what is the difference between high pass and notch filters? Oh, incidentally, C high pass and high pass filters, I show it here. The characteristic curves are exactly the same. Okay, so if I have a C high pass filter or a high pass filter, the characteristics are the same. The key here is If the losses are high and I want to decrease the losses, well, I go to a C high pass filter. It's a more costly filter, more complex, but you're going to eliminate your losses. All right, another question?
Yeah, Paul, new question in the chat. Are there any reasons to use third harmonic filters since this harmonic is primarily zero sequence? Can third harmonic cause resonance?
So for the most part, we have determined that from our experiences, third harmonic filters are not normally required. Your statement that there's zero sequence is, in fact, what we have also seen. So in other words, we've installed a lot of filters. Sometimes we see the resonance creeping back towards a third. We get concerned about it. Normally we have what I would call a backup plan if I do have a third resonance issue. But we have yet to see really this third resonance phenomenon occur. But with that being said, for arc furnace applications, we will often see third harmonic filters. Cycle converter applications, we will see third harmonic filters. So remember, if you have resonance and it's a third harmonic, it can be a positive sequence third harmonic on a system. Very low levels of third harmonic, even if they exist, if we have a third harmonic resonance, it could potentially be an issue. But your statement is the majority of harmonic currents on the system are third harmonic currents are zero sequence. The harmonic filters, medium voltage, 2.4 kV through 38 kV, are ungrounded. So therefore, you'll typically have an interaction between the zero sequence harmonic currents of the third and the harmonic filter. They're non-existent, not an issue. But there are applications, and arc furnaces being one, and cycle converters being the other. All right, so we'll go back to here. High pass and notch filters. So in this case, we have, on the left, we have a system consisting of 3 branches, 5th, 7th, 11th harmonic filter. So 5th, 7th, 11th. And over here, the same exact system, 5th, 7th, 11th. And what you note, though, here is the capacitance values are the same and the millihenry values are the same. The only difference is we've installed a resistor here. And we use a program called EasyPower. We do the simulation and we come up with this impedance scan. And the blue curve represents the notch filters. The red curve represents the high-pass filter branches. And again, they could be C high-pass filters. It would be the same characteristic. And you can see what we've done. The high-pass filter branches has essentially taken out the peaks here. And this is why mine applications, which have interharmonics associated with cycle converters, would use high-pass filter branches, is that we eliminate these resonances, and therefore any interharmonics that might exist are reduced because of the resonant points are being damped, and that's why we call it a damped harmonic filter. So if there are any concerns about non-characteristic harmonics, then high-pass and C high-pass filters are commonly used for that purpose. So we'll talk briefly about tune and detune. We already talked about this a bit. We're just going to, we have two systems, and I tune to different locations. And the top curve here, we're kind of zooming in a bit and looking at, well, what is the difference here? And here we got a 4.7th harmonic filter. You can see at the 5th, and you got to kind of look real close here, there is a value of impedance associated with that filter. And then a detuned filter. And remember, a detuned cap bank, detuned filter, basically what we're talking about is something tuned to a lower frequency, 4.08 for instance, at 6% reactor. You can see there's a higher impedance there. So there is this concept that a detuned filter will not bring in harmonics, but the reality is that it's a current divider. It's just a current divider in this location here. All right, so you can calculate the impedance of the filter at the 5th, if it's a 5.0 tuned filter, and then compare that to that of a detuned filter. And here we're shown that at the 5th harmonic, that tuned filter branch has a 0.16 ohm impedance, and the detuned filter branch has a value of 0.5. So it's only maybe a factor of, I don't know, three times there, to 3 times more impedance. But if I look at the source impedance here, remember we got a current divider current here, the source impedance is 0.517, okay, at the 5th harmonic. So it's really a current division. You can calculate that current division. Do realize that detuned cap banks are subjected to overload, and the common theme of what we hear is, I want a detuned cap bank, I don't have to worry about overload. And the answer is yes, you do, and it really depends upon the division of current here. So I would calculate that. All right. So we're going to go through a problem. I think we have a little bit of time. Do we have time? We'll go through it quick. I wanted to show you some of the ways I would maybe approach a problem like this. So let me go back to that problem, Matt, 1 second, and we'll just talk about it. So we have this would be a common question. I got a 1,000 horsepower drive, a 4.16 kV a drive. It's on a 4.6 kV network. It's a 12-post drive, and the 11th harmonic current is 8%. It's connected to a 69 kV network that has an 8,000 amp symmetrical short circuit current through a step-down transformer, 10 MVA with a short circuit impedance of 7.5%. So you might say, well, what is the voltage distortion? So I'll just kind of walk through how I would approach this problem on paper, and show you what I would do. So the one thing you have is you have I short circuit of 8,000 amps. So in this case, I would say, well, what is that impedance? And so I'm going to kind of shout this out as we walk along. So 69 kV is a line-to-line voltage, so I'll take 69 divided by the square root of 3 to get line to neutral, and that would be 39.8 kV. So V line to neutral equals 39.83 kV, and I would divide that by 8 Ka. So I get kV on top and Ka on the bottom. I would come out with 4.97 ohms. So basically that I short circuit has a Z short circuit of about 4.97 ohms. And this is at 60 hertz, right? I could also, and that's about equal to X also. So remember the X over R might be around 10. So we do have some resistance there. It could be 20 depending upon the spacing and things like that. But you're talking about a very low value of R and a relatively high value of X. The 10 MVA transformer, in this case, I'm going to reflect it to the 4.16 kV bus. So I'm going to take the 4.16 kV, I'm going to square it and divide by 10 MVA. So kV squared on top, MVA on the bottom, the units cancel out, and I end up with a base impedance of 1.73 ohms. So Z base equals 1.73 ohms, and the base impedance is 0.075, so I multiply that times 0.075, and I come up with Z of the transformer, okay, equals 0.1298 ohms, and that's at 13.8 K. At 4.16 kV. So the Z short circuit is at 69 kV. So I got to reflect that through the system. So remember, it reflects through by the transformer ratio squared. So 4.16 squared, 69 kV squared, divide, the multiplier is 0.0036. You can see the value gets pushed way down. So I multiply at 4.97 times the transformer ratio squared, 0.0036, and I get 0.0181 ohms, a very low value. So basically we drew this equivalent circuit already. We got the values of ohms, 0.018 and 0.1298 ohms. And we got the harmonic current injection here. The drive is 1,000 horsepower. I always say 1 horsepower equals 1 kVA. So just quick estimate, 1,000 kVA, 4.16 divide, 1.73 divide. I1 equals 138 amps. All right. And we said the value was, what did we say the value was? Value was 8%, so 0.808 times. So I11 equals 11 amps, about 11.1 amps. So I have to multiply these by 11 because it's at the 11th harmonic. So I got 0.1298 enter 0.018 plus, and I multiply by 11, and I end up with 1.62. So that value of impedance here at the 11th harmonic, okay, is equal to 1.62 ohms at the 11th. So 11.1 amps times 1.62 is the answer. So 11.1 times 1.62, about 18 volts. And that's 18 volts line to neutral. So 18 volts line to neutral. So 18 volts divided by 2400 line to neutral volts would give me the percent voltage distortion. 2400 divide. And that's 0.0075, and that's per unit, so 0.75%. So, so we can switch over. I just want to show you real quick, and I know we're kind of up with time, but let me switch over to a program that I often use, and here's that same problem here, and there, I'm small again. Okay, so here I have the 8 kA short circuit current, the transformer impedance 10 MVA, 7.5%, and I got that drive. If I double click on the drive, you can kind of come over and see the harmonic value, and I got here 11, the 11th harmonic, 8%. Okay, so 8% there. So I got 8% of its fundamental current rating, and if I were to put this into harmonics mode, the one thing that's interesting to click on is I calculate the impedance curve looking from that point, and we were concerned about the 11th. I put the mouse on the 11th, and you can see in the top left right corner 1.62 ohms, and that's over here, 1.62 ohms here. So back to that, 1.62 ohms. So I can also slide this over and kind of scroll down to the 11th and get the same thing, the 11th harmonic, and get 1.62 ohms. So we calculated 1.62 ohms. If you go back, Matt, to that slide, 1.62 ohms. So you can see that you should be able to go to your harmonic analysis program and do exactly what I did here. Whether you're using ETAP or CYME or any of the other programs, you should be able to go through this exercise and replicate, for sure, replicate what you got. If you were to kind of go a little bit further, you could potentially, we could go, I was actually going to do a myth buster too, but we're out of time. So we'll skip that. Maybe we'll do one next week. I'll go through some myths. Let me kind of go to the next slide, Matt. We'll go to the next slide. And
you got to go to PowerPoint.
Oh, PowerPoint's me. I'm the man here. Okay. We kind of went back to the beginning here. There we go. So next week, maybe we'll go through these rules. There's some rules of thumbs. I got the thumb down, and I think the concept here is that these types of rules of thumbs, I think they fail. I actually had a harmonic, I did the simulation for these in the harmonic analysis program. I wanted to walk through and show you how these fail. In particular, this is one from one company I read on the line. Basically, they're saying if the level of the individual harmonics with no PFC system amounts to more than 1.5%, and here I think they're saying 1.5% voltage distortion. They're saying that if the level harmonic voltage distortion with no PFC systems amounts to more than 1.5% for seventh harmonic and higher, or 2% for fifth harmonic, and the resonant frequency of the network can be close to these harmonics, then it must be assumed that these permissible limits will be exceeded by resonance-induced amplification. So in other words, if I install capacitors on this network, so really essentially what they're saying here is if I go out to the network and my plant is currently running at a value that's above 1.5% for seventh harmonic and above, then you better add capacitors as detuned capacitor banks or harmonic filter banks. So I could take that value divided by 10, and I did this in the harmonic analysis program, and I could have a problem because of resonance. So I say this rule of thumb falls apart. There's another rule of thumb that we have seen common is this one here, and it's talking about being careful, and is the total linear load exceeding 20% of the total load? And they say, well, if not, they would propose capacitor banks. If it's greater than 20%, they would propose harmonic filters. And again, we have talked about and have seen what happens when you have resonance. It's value of amps times the impedance of the curve. It really has nothing to do with the percent of load. It's the amount of amps in the system times that resonant impedance that causes the problem. So I think that this one definitely falls apart on you when you do the analysis. So our rule of thumb is do the analysis because it's not hard. If I were to flip over to I'm going to flip back over to EasyPower real quick. To develop a system like this, or to potentially develop a I don't really have a system that I can show you real quick. But to develop a system like this is 5 minutes. It's really about 5 minutes to develop systems, and you could develop something even much more complicated than this in as little as a half hour and come up with a result. So there's really no good reason to use rule of thumbs. Go through the analysis. If you don't have the program, then go through with by hand. It's also not too difficult. So, question.
Yes, new question. Why is the reactor placed at the line side in a harmonic filter instead of the neutral side like in an inrush reactor?
So from our perspective, all of our metal closed solutions, we typically put the inrush reactor and the iron core reactor on the line side. Okay, so the reactor is in series with the capacitor, and whether it's line side or on the bottom, on the other side, it doesn't make a difference. There are some advantages to putting the reactors on the load side, and that is the voltage. If it's an ungrounded reactor and the system is balanced, the voltage to ground is less if the reactor is on the load side of the capacitor. So remember, most of the voltage is dropped across the capacitor, so the reactor will only have roughly 1 over the tuning point squared times the voltage line to neutral dropped across it. So if you bring the reactor to the load side of the capacitor, you have less voltage at that point line to ground. So theoretically, you can go with less insulation on the reactor. But from our standpoint, our designs, we always put the, not always, I would say 98% of the time, we put the transient inrush reactors on the line side. We also put the iron core filter tuning reactors on the line side. There are some other reasons. One might be fault current. You're trying to limit the fault current to the reactor, so you put the capacitor up front. And then if you have some type of fault in the reactor, you would limit the current flow through that reactor, another possibility. But for the most part, what we're doing is line side. We prefer that configuration. And there's some mechanical reasons for why we do it. So just to go through some do's and don'ts, maybe some things that we picked up in the presentation. Understand the harmonic analysis program that you're using. Kind of go through the analysis that I just did. I think is very important. If you can't do it on paper, you're not going to really understand harmonic analysis. So we recommend that you take the time, develop a very simple system, perhaps even the one that we used in this presentation, and replicate it in your harmonic analysis program, whether it's ETAP, CYME, VHARM, PSSU, it doesn't matter, any of those programs, EasyPower, just do it. Because that will teach you, number one, how to get around and how to analyze, well, what are the ohms, what's the current flow, is it in amps, is it in percent, is it VTHD, what is that value? So it really pays to spend the time to dissect the program that you're using and really understand what the output is and what you're reading. And you should be able to replicate it on paper. And once you can do that, you will definitely understand what you're doing. When applying capacitors to a network, always evaluate resonance concerns. Don't go with the notion that I have low harmonic producing devices and therefore I have nothing to worry about. Consider the future load growth. Always consider future load growth. It might be today, a harmonic filter might be designed, but tomorrow or the next day or 10 years from now, they might decide to double the plant capacity, increase the drive load. So always think about load growth. If a facility today does not have any VFD drives or nonlinear loads, it does not mean into the future they will not. If you install a capacitor bank into an industrial plant and what you have done at that point in time, you have dictated that they will never purchase variable speed drives. That's what you've done. Because we have shown that variable speed drives, even when they're low harmonic output, can cause problems with resonance. So by installing capacitor banks in an industrial plant, you're almost dictating that they will not be able to use variable speed drives into the future. And that's something that we would discourage. So our philosophy is you really should strongly consider harmonic filters, or at least the concept of detuned capacitor banks, that 6% reactor concept. When you're doing analysis, always think about the fact that your resonance can shift. The resonance can shift because of the transformer taps, because of the unknown impedance changes in the network, line outages in the transmission network, generation outages in the network. If you have a main tie main, you might drop a transformer, and then you have your secondary loads. The motor short circuit load will cause shifts. So your analysis should always consider these shifts. If you just look at the voltage distortion and current distortion output from the harmonic analysis program, and you do not look at the impedance profile and say, well, what is my possibility of shift? You will without a doubt have some overlook some potential problems. And how well, in the end, does the data that the utility has provided you, how well do they really know it? So that's our recommendation there. Even when you get data from a rectifier supplier or a drive supplier, don't always assume that data is exactly what they say. It is very common that the values will be higher. Their measured harmonic current injection is based upon laboratory test conditions, perfectly balanced conditions, perfectly balanced impedance on the lines, perfectly balanced voltage source, and then they might say, well, I have no fourth harmonic, or I have no fifth, or no seventh because it's a 12-post drive. That's wrong. You should assume that there are some fifth, some seventh. So oftentimes we will see people skip the fifth and seventh harmonic filter, go straight to the 11th because they have a 12-post drive. It's a mistake to do so because there will be fifth and seventh on that network from that 12-post drive. You've got to have fifth and seventh. It's what I would say. You're precluding resonance by putting a small fifth, small seventh, then a large 11th in. So one of the reasons why you would put a filter at the fifth and seventh is to preclude resonance at those points. When in doubt, just do a harmonic analysis. I showed you real quick. I think in the future we will maybe develop a couple models together, and we will show you how fast we could take a system and come up with the value. There's only source impedance, maybe a source capacitor, a transformer incomer, some secondary loads. Really, you can do your analysis very quick, especially if you have the program. Always consume stray capacitance in a network when you do harmonic analysis. There's going to be stray capacitance. It's going to result in resonance up at a high frequency, especially if you're using harmonic filters. So we would suggest that you always assume some type of stray capacitance in your network. And you have to come up with some value estimate. How many thousands of feet or how many miles of cable? You ask your customer, hey, how many thousands of feet of cable do you have? Just put that in your program, come up with KVAR, put it in your model. It's better than nothing. The DOTE is, if you have IEEE 519 compliant drives, don't assume you can add capacitor banks. It's a no-no. You more than likely will still have a problem. Don't mix cap banks and harmonic filter banks on the same system. In fact, when you do that, it's almost guaranteed that you're going to have a resonance issue at the 7th. It's a very common issue. Don't assume filters can be used with standard power factor correction capacitors. Don't assume active filters. So if you have active filters, on your system, you're going to want to use detuned capacitor banks or other filter banks. You want to control your resonance. You can't use a multi-tuned cap bank with an active filter because you're going to cross through resonance, and active filters will have a difficult time as you cross through resonance dealing with that. And don't believe that a detuned capacitor bank is immune to overload. We suggest that you take the time to figure out how much current will flow into that device. So remember, NEPSI resources, our website, the YouTube channel now also has a lot of videos. So many videos outside of what we have here. We have spreadsheet tools and things like that. And the conclusion, we kind of went through that with the do's and don'ts. Today, the code is 345 for PDH credits. Don't forget to tell your colleagues about our tech talks. And we're ready for questions if there are any questions. Okay, guys, no questions. So until next week, we are through. So we're going to do a harmonic filter design next week. I don't think we've done harmonic filter design. So we're going to talk about X of C, how to pick capacitors, how to pick the reactors, how we pick the resistors, the ratings, the standards that are followed, and get into some of those details. We have a spreadsheet tool on our web. So we did a presentation on how to use that tool, but this is going to be more specific, how we rate those values, our recommendations. We tend to be very conservative with our filter design. We're going to talk about that conservatism next week. Essentially, you're paying pennies on a dollar when you come right down to it for that conservatism. Filter banks, a lot of times, are critical to the process that they are being installed on. The system that's actually behind me is an electroweaning plant, and for sure that filter system must run because electroweaning plants utilize large rectifiers, and harmonic distortion and IEEE 519 compliance will be an issue. So they want systems that are 100% reliable. So we're going to be talking about that next week. We'll see you then.